So at the beginning of the last video, I said organic is all about functional groups and their families, and then we went through naming compounds and UV visible spectroscopy and conjugated stuff. What? Yep, organic really is all about functional groups and their families, and we're going to start now, for real, now, about reactions of these functional groups. Alkenes and alkynes, things with pi bonds. Things with pi bonds undergo what's called addition reactions. Addition reactions are like this. Alkene has a pi bond breaks to become a single bond, and something gets added across that pi bond. Something gets added on one side, and something gets added on the other side. We're going to go through a lot of reactions of this type, so we'll see a lot of what I mean. But sometimes Y and Z are different things, and sometimes Y and Z are the same things. Okay. Alkenes commonly do electrophilic additions. What does that mean? Alkenes themselves are nucleophiles because alkenes have extra electron density in the middle. Remember when we said that a long time ago? Alkenes have extra electron density in the middle due to their pi bond. So alkenes are nucleophiles. The nucleophile adds to an electrophile. So this YZ thing, at least some atom on this YZ thing, has to be an electrophile. Something on that molecule has to be electron deficient. Alkene, have pair, will share. Electrophile, ready to receive electrons. Remember, Lewis acids, Lewis bases, but we're going to use this electrophile, nucleophile terminology much more now. Alkenes, alkynes, things with pi bonds are nucleophiles. Okay, let's see how it works with a very specific example of how a reaction between an alkene and HBr, this is HCl, an alkene and HCl, how does it work? That means let's draw a mechanism. A mechanism is showing curved arrows and all involved intermediates. All right. Electrons go from the nucleophile to the electrophile. How did I know I needed to attack H and not Cl? Well, this goes back to dipoles. There's a dipole on HCl pointed toward the chlorine, away from the H, giving the H a partial positive charge and the chlorine a partial negative charge. The electrophiles, characteristics of electrophiles is that they have positive charges or partial positive charges. So between H and Cl, H is the partial positive, nucleophile attacks electrophile. So that red arrow is telling me there's a bond that's going to be made between carbon and hydrogen. Hydrogen can only make one bond at a time, so we have to break the HCl bond as well. So the product of those arrows I just drew are the CC double bond is now a single bond. The CH3s, they're all still there. But I've made a new bond from carbon to hydrogen. And chlorine is off floating by himself now because he broke away from the hydrogen. That's not good enough. That's not finished. When the chlorine was connected to the hydrogen, we didn't draw it because we're organic chemists and we leave off things like electrons all the time. But chlorine had all of these electrons when he was connected to hydrogen. Then that red arrow says he was given an extra pair. So chlorine is not chlorine, he's chloride. He's an anion. The two carbons that were in the pi bond had 4 bonds. They were neutral. Now this carbon still has 4 bonds, but that one does not. That one has only 3 bonds. Carbon's in group 4. 4 minus 3. This carbon is plus. So those two curved arrows make these products as intermediates. This is not the final product. This is not the end of the story. We've got to do more. Carbon is unhappy. He's got a positive. Chlorine is kind of unhappy. He's got a negative. Hook those guys up. Chlorine is now my nucleophile, and he attacks the carbon that has the positive, because electrophiles have positives and partial positives. So I end up making this. New H over there, Cl over here. If I wanted to fancy in all these dots, I can do that. Yep. Just because I think it's kind of worth it. How would you draw this mechanism if you hadn't drawn all the carbons, all the hydrogens, all the things? An organic chemist, after some practice, would draw it like this. And you say, what's the difference? Well, up here, I showed every carbon and hydrogen explicitly. Over here, not so much. Over here, I explicitly showed which carbon that hydrogen got connected to. Over here, I assumed, since the plus is on that carbon, it must mean the H joined up with the other carbon. And then chloride attacked just like before. Here's my stick model. Do you have to be great at the stick model today? No, but we're going to start drawing stick models soon and very soon, rather than all the C's and H's like this. You are welcome to draw it as all C's and all H's always and forever, but I will usually, almost always, draw it on this purple version because it takes a lot of time to draw carbons and hydrogens. Alright. There's a little plea at the bottom of the set page that says, please read these pages. It's all about curved arrows. So a little soapbox for a moment. Curved arrows are a big deal to organic chemists. Curved arrows are a big deal to organic chemists. We have points on every test designated to whether your curved arrows are correct or incorrect. So if you learn the rules on curved arrows now, you will save yourself lots of headache as you continue throughout the course, because we're going to draw so many curved arrows. Alright, that's enough. So keep these things in mind as we draw a reaction coordinate diagram of that reaction. So we'll put us a little graph up there. Reaction progress. And energy on the y-axis. Assuming this reaction is exergonic, that's going to allow me to put a shelf of reactants. That's these guys. And products. That's this guy. I should not simply connect these with a hump. Nope. That's assuming this is a one-step reaction. It's not. This is a two-step reaction where there's an intermediate in the middle. An intermediate known as a carbocation. I should have actually pointed that out while we were drawing our mechanism. I don't know why I didn't. Silly me. That intermediate has to be on a shelf all on his own. Well, it's the carbocation and chloride ion, actually. They need to be on a shelf all on their own because they are observed throughout the process of the reaction. Those shelves should be connected with humps and lumps and bumps, like that. That's hard to see, I know. Poor planning. There are two humps in this reaction. At the top of each hump is called a transition state. That double dagger thing right here, that means transition state. So there's a transition state up here, and one up there that I just have no real estate above to write one. The transition state is the actual process of making and breaking bonds. So you could draw in that very top transition state up there that the alkene bond is starting to be broken, so I'm dashing the alkene bond. And I'm starting to make a bond to the hydrogen, and I'm starting to break the hydrogen-chlorine bond. So the bonds that you're making and breaking should be little dashy bonds in transition states. You could draw the transition state for this other one as, we're doing only the stick model this time, the chlorine-carbon bond is dashy. You can put partial charges on transition states and stuff. We won't really draw a ton of transition states in this class, but that's what transition states are. It's electrons moving around, shifting to make and break new bonds. So I should not have drawn that transition state directly smack dab in the middle, but we can work around it, I guess. The energy difference between the energy shelf of the reactants and the energy shelf level of the products, that's delta G, assuming the scale over here is G. Sometimes the scale over there is H, so that would be delta H. And I said that the reaction was exergonic. Exergonic just means negative delta G. So that means products should be at a lower shelf than reactants. Reactants to products, exergonic. Reactants to products that way, endergonic. Positive delta G, endergonic. I don't have room. From the reactant shelf energy to the top of the transition state hill, that's called the activation energy. And both of these steps have activation energies. So we'll name it EA1 and EA2. EA1 is larger than EA2. Okay, cool. What does that mean? The hill of the top of the transition state that's highest. Of the two transition states, that's the highest. The hill that's the highest is called the rate determining step. The hill that's the highest determines the rate determining step. So this is a two-step mechanism. Alkene to carbocation, step 1. Carbocation to product, step 2. The first step is rate determining. I know that on this reaction coordinate because that hump is the highest. But I'm going to also say any reaction involving making, this is getting totally illegible, carbocation, formation of the carbocation, I'm going to put it as a C+, that's carbocation. Formation of the carbocation is the rate determining step. So if I were to ask you to draw a reaction coordinate diagram for a certain reaction that makes a carbocation, you know the activation energy of the step that makes the carbocation should be the highest hump on your graph. We cool? Good thing I don't get feedback instantaneously. Here's a bunch of words about reaction coordinate diagrams. I think we kind of covered that. I think we kind of covered that too. Yeah? Maybe we didn't say this last little bit. The more stable the transition state, the faster that step. So that means the smaller the hill, the faster that step is. Alright. There's this fancy thing called the Hammond postulate. Oops. The Hammond postulate simply says a transition state is more similar in structure to the species that is closer to energetically. So if you had something that looks like this, the top of the hill is closer in energy to the reactant, so the transition state looks more like the reactant than it does the product. If you have the opposite, this versus this, the transition state looks more like the product. That's what that says. This step is exer, this step is ender. Hammond postulate's fancy words, but simple concept. I trust you. There's words we already said, ender, exer, what they mean. So alkenes do additions. Alkenes do electrophilic additions. We've drawn a mechanism of an alkene adding to HCl once. Let's do it 3 more times. So I'm going off to the races, drawing a mechanism. Hopefully you could do the same if you are following along. I'm going to do it in the traditional organic way without all the C's and H's shown. I probably could and maybe should show explicitly where the hydrogen got added, but there's my product. How did I know that that's what I was supposed to do? Well, again, it's all about functional groups. And these things that I'm drawing are all alkenes. So I was taking for granted that the first thing I'm really doing is analyzing what functional group I'm trying to react and what I'm reacting with. Note, I know this is the only reaction you've learned so far, / you're still working on learning now, but the first process, the first step, when we're going to learn at least 10 before the next test, is to analyze what functional group you're working with and what you're adding to it. So all of those go through a familiar, similar, same intermediate known as a carbocation, and all of those end up making an alkyl halide as the product. You should start trying to group together reactions, not just by what family they're under, but what kind of intermediates do they go through and what kinds of products do you get out of them. So we drew those 3 mechanisms. I drew it lightning fast. Why does it matter? Why should you care about the mechanism? Well, alkenes are nucleophiles, and if alkenes react with acid, acid is an electrophile, so an alkene will react with an acid to make a carbocation. If there's a carbocation present, that carbocation then reacts with an additional nucleophile. And in all 4 examples we've seen so far, the nucleophile was a chloride. But it could be another halogen. The nucleophile could also be water, or an alcohol, or a carboxylic acid, or a thiol, or a different alkene, or other, or. Lots of things can be nucleophiles and electrophiles, and so if you understand the mechanisms, the processes of how and why reactions do what they do, I can give you unknowns, I will give you unknowns, give you reactions you have never seen before, and expect you to be able to draw what should happen based on the foundation that we're building with our mechanisms. Doesn't that sound like fun? Yeah. Okay, here's an alkene. Off to the races. Pi bond attacks the H. HCl bond breaks. And then I make an intermediate carbocation. And I say, whoop, I have trouble here. Should the H get added on this side and I make that carbocation? Or should the H get added on this side? Oh, that's an H, that's an H. And I make this carbocation. How do I know? If we go through and classify the type of carbocation we have here, this blue carbocation is a carbon connected to 3 other carbons. What kind of carbon is that? It's a tertiary carbon, therefore that's a tertiary carbocation. This carbon is connected to only 1 other carbon, so that's a primary carbocation. The rules are, in general, a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, which is more stable than a methyl. Let's not even really talk about methyl. So because a tertiary carbocation is more stable, that means it forms faster. What does that matter? What does it mean? Why do I care? If I drew a little reaction coordinate, I've got my alkene and HCl on a reactant shelf. And then I can have the blue carbocation on one shelf and the green carbocation on a different shelf. The green should be on a higher shelf because a primary carbocation is less stable than a tertiary carbocation. Lower energy means more stable. So I realize it's kind of squishy up there, but The tertiary carbocation is lower energy. Lower energy is going to lead to a lower activation barrier to get to the blue than to the green. Lower activation barrier means happens faster. So, in summation, the blue carbocation is the carbocation that forms, not the green. We'll erase that one. The blue carbocation is the one that forms, so chloride attacks that carbocation, and you get this as your only product. You do not get any of this as a product, where chlorine is on that primary carbon. You don't make any of that. Okay. If you walk back through those last 4 examples and you analyze the carbocation in each, there was no difference. What? Over here and over there have different substituents. If we go back and look at these carbocations, this carbon and that carbon have the same substituents. My laser's not showing up there. The top alkene has the same substituents on both sides. The middle alkene has the same substituents on both sides. The bottom alkene has the same substituents on both sides. So what that means is the regiochemistry didn't matter. Wait, what? Regiochemistry means which region of the molecule gets the H and which region of the molecule gets the Cl. Also known as, does the H go here? Does the H go there? Does the Cl go here? Does the Cl go there? When you have an alkene that's not symmetric, you must consider regiochemistry. There was a guy that talked a lot about regiochemistry, and his name was Markovnikov. Markovnikov, Hungarian chemist that studied a lot of alkenes, and said, it seems that I make the most stable carbocation most of the time when the H's go with H's. What? Markovnikov said, it seems I make the most stable carbocation when the H's go with the H's. Meaning, this carbon of the alkene in the beginning had 2 hydrogens. This carbon of the alkene in the beginning had 0 hydrogens. So Markovnikov says, put the H with the H, and you will probably make the most stable carbocation. So I put the H on the side that had 2 H's, and that's how I made the blue carbocation. The green carbocation came from putting the H on the carbon that didn't have any H's. That's how I knew it was not good. Markovnikov's rule is simple and helpful, but it's not quite always right. Okay, you've been warned. Alright, carbocations are a big deal. We will talk lots about carbocations, not just for this unit. We will talk lots about carbocations from here until the end of your organic journey whenever you decide to hop off that wagon. Carbocations are usually classified as methyl, primary, secondary, or tertiary. A methyl carbocation simply means a CH3 with a plus. They are terrible. Oh, my Lanta. I just wrote that backwards. They are terrible. Methyl carbocations are the least stable of all of the carbocations. Tertiary is the best of the simple carbocations. What do I mean? Simple carbocations, these are not. Allylic and benzylic, those are terms that I have not exactly heard before. Allylic means next door to a pi bond. Benzylic means next door to a benzene. What does it mean to be next door? Not directly connected to the pi bond, but on the carbon that is directly connected. What? Yeah. This is an alkene, and here's a carbon connected to that alkene. If that carbon connected to the alkene has a positive, that's an allylic carbocation. Here's benzene. Here's a carbon that's directly connected to benzene. If that carbon has a carbocation, that's called a benzylic carbocation. Allylic and benzylic carbocations are great. Any idea why allylic and benzylic carbocations might be great? Ideas? Nobody? It's because of resonance. Yep. Resonance of that pi bond helps to stabilize that carbocation. Resonance of that pi bond helps to stabilize that carbocation. I could draw lots more resonance of the benzylic one over here. So allylic carbocations always have 2 resonance contributors. At least. There could be other things connected that help out even more. Benzylic carbocations always have more than 2. So who do you think is more stable, allylic or benzylic? Benzylic is more stable than allylic because you have more resonance in benzylic carbocations. Okay, these carbocations are both are allylic and benzylic, but you also need to classify them according to being primary, secondary, and tertiary. So this is a primary allylic carbocation. This is a primary benzylic carbocation. So tertiary is more stable than secondary, is more stable than primary. Benzylic is more stable than allylic. What if you had something that's tertiary and allylic compared to something that's secondary and allylic? Well, something tertiary and allylic is more stable than something that's secondary and allylic. Oh, yeah, okay. Vinyl and aryl. I'm going to draw those in red because vinyl and aryl are no good. We just mentioned what vinyl was in the last video. That is a vinyl carbocation. It's not on the carbon attached to the double bond. It's on the carbon that is the double bond carbon. Aryl is like benzylic but bad. Aryl means a positive charge, a carbocation, on a benzene, directly connected to a benzene. Those things are terrible. Terrible. Really bad. Don't do that. Okay. Carbocations are things we'll see all the time. Carbocations are all sp3 hybridized. That means they have trigonal planar geometry, and that's going to mean some stuff about stereochemistry momentarily. Okay. So far, I've just said that tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. Here are the electrostatic potential maps of all of those things I just listed, from a tertiary carbocation over here, all the way down to a methyl carbocation over there. Methyl carbocation is bright blue. That means it has very low electron density. The tertiary has more electron density than the methyl, for sure. So things that are positively charged, if you can have electron donating groups, if you can have electron donating groups around something that's positively charged, it helps to stabilize your positive charge. So, apparently, carbon groups being around a carbocation can help stabilize the positive charge. How do those carbon groups help stabilize the positive? Through something called hyperconjugation. Hyperconjugation is donation, electron donation through sigma bonds. Resonance is electron donation through pi bonds and pi systems. Hyperconjugation is electron donation through sigma bonds. So something that's primary, a carbocation that's primary, has these three sigma bonds that can help donate and stabilize this carbocation. Sigma bonds need to be on the neighboring carbon. Should have said that already. Something that's secondary has these sigma bonds that can help stabilize, I forgot my positive charge, that can help stabilize this positive charge. So the top model has 3 sigma bonds that can help donate. The bottom has 6 sigma bonds that it can help donate. Any idea how many bonds, sigma bonds, a tertiary carbocation would have? 9. So the more sigma bonds you have next door, the more spread out that positive charge becomes due to hyperconjugation delocalization, sharing through sigma bonds. Hyperconjugation is kind of a confusing concept, but when I ask you, why is a tertiary carbocation more stable than a secondary, you're going to tell me because of hyperconjugation. Yeah? Okay. So I've told you the class was cumulative, but you weren't quite a believer until I say, remember all that resonance stuff we learned a little while back? Yeah, it's all coming back. Because if a group can donate to a carbocation, whether through hyperconjugation or through resonance, that makes the carbocation more stable. If a group withdraws from a carbocation, like through resonance or induction, that makes the carbocation less stable. So resonance and induction, where we talked about acids and bases, all still fair game for talking about carbocations. Let's recap inductive effects first. Remember, inductive effects is electron withdrawal through sigma bonds. So by that logic, hyperconjugation and induction are similar effects. Induction is withdrawal, hyperconjugation is donation, but both of those operate through sigma bonds. So they're kind of two ends on a scale of good and bad, donation, withdrawal. Hyperconjugation is good for carbocations because it's donation through sigma bonds. Induction is withdrawal through sigma bonds, so that's bad for carbocations. Yeah? Well, let's talk about induction as it applies to these couple of examples. But wait, we haven't drawn these mechanisms before. You're right, we haven't. But based on some characteristics, I'm going to teach you how to approach problems that you've never seen before. If I analyze, I have an alkene, that's a nucleophile. I have water, that's an I don't know. I have H2SO4, that's sulfuric acid. HCl is hydrochloric acid. H2SO4 is sulfuric acid. So this I'm going to classify as acid and water addition. So alkenes are nucleophiles, acids are electrophiles. So the first arrow for my HCl addition was alkene attacks the acid. So my alkene is going to attack the H of my acid. H can only make one bond, so I dump electrons onto the O. That makes the H get added here because Markovnikov said so. Be careful. That makes the H get added here because that gives me a carbocation up there that's what variety? Secondary. This carbocation is a secondary carbocation. If I had added the H up there, the carbocation would have been down here. That would have been primary. So secondary carbocation, more stable than primary. When you're doing acid additions like these, you should always make the more stable carbocation. Sometimes Markovnikov didn't quite get it right. He only studied simple carbocations. So, Markovnikov is helpful, but we're going to say, make the more stable carbocation. As it turns out, this is a Markovnikov carbocation. Okay, so then I need to find a nucleophile to attack my carbocation. The nucleophile that can attack is water. Have a pair, we'll share. Water is my nucleophile, and it attacks my carbocation. When he attacks my carbocation, he brings both hydrogen buddies along for the ride. Oxygen donated a pair to the carbocation. He's still got one pair left over, and oxygen is now making more bonds than he would prefer, so he gets a positive charge. If this were chloride, chloride would attack and be done. We're not done. Because I have a product that still has a positive charge, I need to clean up. Clean up, clean up. Everybody clean up. I'm going to take another water molecule and attack one of the hydrogens. Because if I attack one of the hydrogens, that allows me to turn loose of the electrons that were holding the hydrogen to the oxygen, which allows me to get a neutral oxygen compound. I made an alcohol. Yeah. Yeah. Okay, so tell me again, why do mechanisms matter? Why do we care? Well, before we move on to the second example, if I recognize I'm reacting with an alkene, alkenes are nucleophiles, so my first mission is find an electrophile for that alkene to attack. Done. I found an acid. That made a very familiar intermediate known as a carbocation. Carbocations are fantastic electrophiles. So now that I have an electrophile in step 2 here, I need to find a nucleophile. Have pair will share. I'm looking for a lone pair of electrons. Oh look, water's got one. Water is a good nucleophile. The only thing is when water attacks, he brings along both hydrogens with him and gives you a positively charged product. That's not good as a final product, so you have to go through one more step to clean up and get you a neutral product overall. The mechanism is so similar to the HCl mechanism, but it's slightly different because water had an extra proton hanging onto him that you had to clean up. So what? It makes this a 3-step mechanism instead of a 2-step mechanism. That's all. Alright, I'm ready for the next one. I have an alkene. I'm looking for a nucleophile. Nope, I'm looking for an electrophile. The alkene is my nucleophile. I got acid. I'm gonna grab an H off of that acid. And when I grab an H off of that acid, I'm going to make a carbocation. If I make a secondary carbocation like that, you assess for a moment the stability of that carbocation that's blue and this carbocation that's orange. The orange carbocation is a primary carbocation. In general, secondary is more stable than primary. Well, that's when you have simple carbocations. All these fluorines over here make this molecule far from simple. What are all these fluorines about? Well, what was our... what are all these fluorines? All those fluorines are withdrawing electrons from the carbocation. So you want the carbocation to be as far away as possible from the fluorines because that makes it more stable. So are we going blue or are we going orange? We're going orange. The orange carbocation is more stable than the blue carbocation because of induction. Induction is withdrawal and withdrawal is bad. Orange has less induction. Alright, so I redrew it all. There's my carbocation. Carbocations are fantastic electrophiles, so I'm on the hunt for a nucleophile. I'm on the hunt for someone that has pair, ready to share. Oh look, the oxygen in ethanol has a lone pair. It's ready to share. So I get to this. I should have turned it back orange, but oops. This carbon down here at the bottom, a lot of students, when they're trying to draw this on their own, I do encourage, strongly encourage you trying to draw this on your own. Don't forget him. He's important. He's there. Don't neglect him. Okay, so when ethanol attacked, it brought along 1 hydrogen and 2 little carbons. It's a positively charged thing. So how am I going to get to my final uncharged product? Oh, we're going to try to squeeze it up above. Ethanol in this reaction and water in the top reaction are the solvent of these things. What that means is there are a lot of ethanol molecules around, a lot of them. There are a lot of water molecules in the top example around. So that's why I could just pull another water molecule out of thin air and it attacks that hydrogen. That's why I could just pull another ethanol out of thin air and it attacks that hydrogen. It's not that there's only 1 molecule of ethanol in here. There's maybe a mole of ethanol, maybe 10 moles of ethanol, maybe more. There's a ton of ethanol molecules. So I can use 1 ethanol to clean up my product and get this final product in the end. That product in the blue circle is an anti-Markovnikov product because it did not make the product that Markovnikov would have predicted. Remember, Markovnikov talked about simple alkenes and all those fluorines. That's far from a simple alkene. Yeah? Whew, yeah. So we've officially learned 3 mechanisms, I guess, at this point. HCl additions, but really that could be HCl or HBr or HI. It's all the same dang thing. We've learned acid and water additions. We've learned acid and alcohol additions. Do I think it's worth your brain power to kind of memorize those things as a list? No way. You know I'm not a fan of memorizing. I think it's good to categorize all of those things as acid additions to alkenes, and acid additions to alkenes go through carbocation intermediates. I'm making the most stable carbocation I can, and a lot of times that means the Markovnikov carbocation, but not always. And then once I have a carbocation, I'm looking for something that has a pair and is ready to share, and I need to make sure that I have a neutral product in the end if at all possible. Don't I make that sound simple? Huh, yeah, it's great. That was a couple of examples to talk about induction and compare induction when there is not any and when there is some. Resonance also affects carbocations. Resonance can make carbocations better. Resonance can make carbocations worse. It depends on whether it's resonance that donates to the carbocation, that makes it better, or resonance that withdraws from the carbocation, that makes it worse. Okay? Here are 4 carbocations for your viewing pleasure. Pause. Please, I beg you, pause and figure out how you would rank these carbocations from most stable to least stable. Please pause and try it. It's worth your effort. You got it? Did you really do it? I hope so. Well, let's talk about what makes each of these good and bad. In A, that carbocation in A is a secondary carbocation. Did you know that it was secondary, or did you call it tertiary? That's a secondary carbocation because oxygen does not count. B, that carbocation in B is a secondary carbocation. That one seemed more obvious. C, that's a secondary carbocation as well. D, that's a tertiary carbocation. So if that's the first analysis you did, that would lead a lot of people to saying D is the most stable, and I say, nah, it's not. D would be most stable if these were simple carbocations. But when I've got this ester functional group hanging out over here, these are not so simple carbocations. So I have to consider other factors first, and then I can consider tertiary, secondary kind of stuff. So A has an oxygen directly connected to that carbon that is the carbocation. What can that do for me? That oxygen can donate by resonance to get me this resonance structure. And that resonance structure, the green one versus the black one, which one's the winner, chicken dinner, more, better, bigger contributor to the hybrid? The green one is actually a more significant resonance contributor because everybody's got an octet. So the A carbocation seems pretty grand because it has resonance that stabilizes that carbocation. You see that that lone pair is donating toward the carbocation? That's good news. Okay, well, let me point out something on the bad end of the spectrum. In D, D doesn't have any resonance that can help donate to the carbocation. D, I could come up with some resonance that would look like this. And you say, I say the same. Yeah, that's not pretty. Not pretty at all. This one has a carbocation in my resonance picture next door to another carbocation. Oh my, that's terrible. That's awful. This carbon, as in that carbon is partially positive. The reason I know that carbon is partially positive is because this resonance structure exists. So if I drew the hybrid, there would be a partial positive on this carbon down here. Partial positive next door to a carbocation, that's awful. It's really bad. Okay, so A has resonance that makes it more stable. D actually has resonance that makes it less stable. A has resonance that donates toward the carbocation. D has resonance that sort of pulls away from the carbocation. It doesn't directly, but kind of pulls away from the carbocation. So D is actually the worst. Of all four of these, D is the worst. You say, but he was tertiary. He's the worst. All right, it's time to discuss B and C. B and C, you could draw resonance within the esters on both of them, but that doesn't really help me decide whether the carbocation is more or less stable. As in, the resonance over here is not directly affecting the carbocation, so we're not worried about resonance in B or C. We're worried about induction in B and C. In B and C, who experiences more induction, a stronger inductive effect? Which carbocation is closer to electronegative stuff? B. The oxygen is like 2 bonds away in B. The oxygens are like 3 bonds away in C. So induction, remember, has to operate through sigma bonds, so you're really kind of counting how many sigma bonds between the carbocation and the electronegative atoms. So there are more bonds between the carbocation and electronegative atoms in C than there are in B. So my final ranking is A is the best, C is next because it doesn't have induction as close, B is after that because it's got more induction than C, and D is the worst. So this was not, these questions were not about hyperconjugation. These questions were about induction and resonance. How do you know if it's a simple tertiary is more stable than secondary kind of question versus a complicated resonance, induction, all this stuff? If you have functional groups connected to your carbocation or to your molecule that are not carbon, meaning alkane stuff, we've got an ester here, if you had an alcohol, if you had some functional group connected to your molecule other than just alkane carbons or alkene carbons, then it's not going to be a simple Markovnikov, anti-Markovnikov thing. If you have other functional groups, you're probably supposed to be considering resonance and induction when you're analyzing that and drawing that problem stuff. Whew. Resonance versus induction, which one's more important? Well, they often compete. In general, resonance is more important, but occasionally induction is more important. As we work through more examples, as you really get good at this organic thing, it will become a little bit more obvious. Delocalized electrons can affect the reactivity of a compound. This should be a complete sentence that says, rank the following molecules in order of relative reactivity toward HBr. What? Which one of these molecules reacts with HBr the fastest? When I ask about speed, it's really asking about stability. So we've drawn a couple of little baby reaction coordinate diagrams. And if you're comparing things that are on like that black shelf versus a red shelf, the black shelf is lower, so more stable. This middle black shelf. This is lower, so it's more stable. And how do you get to be on that black shelf? A more stable carbocation is lower energy than a less stable carbocation. Oh, that's enlightening. So we're looking, when it says rank the relative reactivities toward HBr, we're looking for carbocation stability. That's exactly what this question is asking. In this first one, in A, my carbocation would be here, potentially. In B, my carbocation would be here, at least potentially. In C, if I want to stay similar, my carbocation would be here. One of them is a simple Markovnikov carbocation. Who dat? That's B. B is a simple Markovnikov carbocation. It's just a tertiary carbocation. There's no extra resonance, there's no extra induction, There's no extra junk to consider. A and C are not simple carbocations. There is extra junk to consider. In A, does that oxygen help or hurt your carbocation? In C, does that oxygen help or hurt your carbocation? In one of them it helps, in one of them it hurts. Who's who? In A, it can donate to make you this kind of resonance picture. And if we consider those, who's the winner chicken dinner? This one, because everybody has an octet. In C, it must mean the oxygen hinders that carbocation, making it worse. It hinders because of induction. There's no way that this lone pair can share with that positive charge. It's too far away. So, A is a secondary carbocation that has resonance that makes it good. B is a simple tertiary carbocation. C is a tertiary carbocation that has induction. The ranking is like that. Secondary with resonance is better than tertiary without resonance. Tertiary without resonance and with no other functional groups is better than tertiary that experiences induction. So, molecule A reacts fastest with HBr, molecule C reacts slowest with HBr, and B is obviously in the middle. Again, when I say what reacts fastest, the underlying question is, which thing makes the most stable carbocation? I'm going to put letters on these, and you have to vote. That's all.